We are going to talk about fast lane to AI, how you go from ideation to production in weeks. I'm Saurabh Giri. I'm the Chief Product and Technology Officer of Voltage Park. With me here today is Raga, Distinguished Engineer. In this session, we are going to distill some practical lessons from having done this several times, both at Voltage Park and also the engineering team at Voltage Park was involved in building Amazon's AI platform. So we've seen this at scale with thousands of customers in their journeys from ideation to production. And we've distilled down just a few lessons as much as we can fit in 20 minutes. Obviously, everything is more complicated than it is, but these I think you will find useful. Voltage Park is a cloud service provider that specializes in AI workloads. Our mission is to make it easy for builders to build AI products and for companies to consume them. On the builder side, we work with startups, very startup friendly, world-class hardware service at very reasonable cost. We work with companies that are trying to go from ideation to production. The way we do it is something that we call our AI factory. We'll talk about it briefly. That's not the main point of this discussion, but we'll talk about it briefly later. We are one of few CSPs in the US that own and operate GPUs at scale. We are in 6 data centers today, 2 offices, and our footprint is very quickly expanding. Some of the most sophisticated model builders today, household names, the sort of people, if you drive down 101 freeway in the Bay Area, the sort of people you see on billboards, they are our customers. So you may not have heard of us, but the people who are pushing the edge of what's possible in AI today, they have heard of us and they are our customers. So let's get to the main content. This is all based on a real customer example. For privacy reasons, we switched around the facts a little bit for anonymity. But this is a real customer use case where we went from nothing to production within weeks. Raga, would you like to frame?
Hey, yeah. So this customer has thousands of CCTV cameras installed on their premises. They have what we would call a very passive video. And the requirement from this customer was, how can we shift this passive system into something that is a little bit more active and easier for the human operators to use and evaluate. For example, a very specific type of query that the customer wanted to get answered was, show me the snippets of surveillance footage that shows a car, but not a truck, entering a gate between 2 a.m. and 4 a.m. Now, obviously, to do this in their existing system involves hundreds of hours of sifting through video footage, and that obviously did not scale. And that's basically why they decided to apply AI to this particular use case.
And that brings us to lesson number 1. It's very important to decompose the end-to-end problem. A mistake that a lot of people make is in trying to solve everything in one shot and one go perfectly. And if you try to do that, inevitably, most of the time you'll realize that you end up with a system, a solution that's over-engineered and over-complicated and overly expensive. So it's very important to break it down. And the next thing is also quite important. It's very important to be thoughtful about in which of these steps is the AI actually useful. Trying to use AI in situations where non-AI is perfectly fine results in a system where, for example, you're trying to use one grand model to solve everything end to end, and then you're stuck with inevitable trade-offs, such as?
Yeah, so let's assume in this case, you all might have been very familiar. The current state of frontier model technologies that they are very good at image understanding, video understanding. The same model can also reason about the particular query that you have. And we could have easily built this using one gigantic model, pumped the data straight to it, gotten back our results. But as you will see through the lessons learned, that often leads to unexpected outcomes, fragility in system, exploding costs, and somewhat of a black boxy system that then you're not able to control and maintain in a long enough duration of time. For this particular use case, we broke down the problem into roughly 3 large components. There's the C, filter, and reason. We wanted a model that would be able to just do only object identification, not reason about anything, just draw bounding boxes around objects and class labels that we've defined. We needed a filtering system that would basically weed out large chunks of the video that are no longer relevant or have nothing to do with the query at hand. And then at last, we actually needed a reasoning system that would then take the customer natural language query and then try to match it to the scenario description that has been seen and filtered by the previous steps in the pipeline. And by breaking down this into subcomponents and designing it as a system, what we ended up accomplishing was having 3 separate containerized environments that all can individually scale independently. So for example, if the customer decided to double their CCTV footage or the number of cameras involved, we could horizontally scale the number of object identification and filtration systems. We could control the amount of batch queries that go into our reasoning models as the last step. And it gives us a lot of flexibility on how we can define the system as opposed to trying to use one gigantic model where all these 3 steps are kind of subsumed within it.
Lesson number 2, match the hardware to the model. What does this even mean? Why are we talking about hardware all of a sudden? The answer is, until you finish a POC, you don't really fully appreciate how expensive it is to use AI in production. So if you don't design the end-to-end system, keeping in mind from the beginning, how can I do it as inexpensively as possible, you will find out after the POC that it is quite expensive, and then suddenly cost becomes a bottleneck to scaling out in production.
And this manifests in several ways, right? And I think it also ties back to one other point that we made at the beginning of this talk, which is you first have to pick the right models. For object identification, we use the tried and tested model that's not even transformer or diffusion based. It's existed for a really long time. It's a battle-tested model that can draw bounding boxes around CCTV footage images. But it's an extremely small model, and we didn't want to waste precious H100 capacity on hosting these models. And there we employed different techniques like packing n number of model copies onto a single GPU. You could also explore the possibility of using A100s or previous generation hardware to host some of these smaller and simpler models, and then you right size your available capacity for the the powerful LLMs, and of course obviously the filtering requires some amount of GPU capacity as well. In doing so, what you are trying to accomplish is to say what is your minimum hardware footprint that is required to host this pipeline. And as you will see in the subsequent slides, this requires some amount of tuning and a lot of experimentation to get the resource allocation right.
Lesson number 3. So if you connect the dots between the first 2 lessons, inevitably for a lot of use cases, non-trivial use cases, you'll find that you end up using a few open source models. And then if you're doing that, the important thing is to begin with the right domain adapted open source model for that step, for that component. And then you have to customize it with actual production data. And right here is where many projects get stuck, because data is messy. You have to curate the data. You have to think about things like, in many enterprises, compliance, audit trails, all of that. It's messy. So if you do a project a sequential way, then immediately you're adding weeks, if not months. So I think the meta point here is every project has things that can be done quickly and then things that take time. As soon as you hit something that takes time, it's important to find a simplifier that lets you get started, even if it's not perfect. So you get started, you iterate with something that works, and then you iterate until you get it to where you want it to be. How did we, what simplifier did we do for this one?
Yeah, so in this case, usage of synthetic data helped us in numerous ways, and I'll go through them in a rough sequence. Handling something as sensitive as CCTV footage has to be done with extreme care, especially if this is your customer's data. They are worried about who's handling this. We have to be careful about how we are storing this. So as Saurabh mentioned, this can be a weeks or even month-long effort to just get started in procurement of the first tranche of data. We sidestepped all of this, and we immediately started to do synthetic video generation. The state of the art in video generation today is pretty advanced, and you have open source models that can actually produce very, very realistic synthetic CCTV footage. In fact, at the beginning of the slides, if you had seen the graphic, that's an actual synthetic generated CCTV footage. None of the people on that video are real. The place is not a real place. But it has gone through our pipeline, which has done the object identification and the scenario description evaluations. To begin with, it unblocks our development pipeline. So we are able to just generate synthetic data. We are able to build the 3 steps of our pipeline. Our devs are not kind of waiting for how to proceed and what to test and tune and so on and so forth. The second thing it unblocks is our ability to test. With synthetic data, we are able to simulate different scenarios of CCTV footage. We can increase how grainy the footage is, the various angles, interruptions, objects, loss of resolution, quality, foggy images. All of these now can be tested, and we start to make our system more resilient to what will be eventually the actual conditions of the CCTV footage that we're going to get from our end customers. The last part is once you have synthetic data and once you're feeding it through your system, you can actually simulate an at-scale test. And that's very important, and it connects back to the slide just before. You need to know your hardware footprint. You need to be able to tune and allocate the right amount of resources to the various models in your pipeline. So once you have synthetic data and once you start pushing it through your system, you start to identify what are the bottlenecks. Where is the actual systemic bottlenecks? Is it the hardware problem? Are the models being efficient? Is the sufficient memory available for the context? So on and so forth. And we largely de-risk the project in this way by just relying a lot on our synthetic data set.
Lesson number 4, any software system that uses AI, even in a single place, is inherently non-deterministic. You have to accept that and make peace with it. It's very tempting to be impressed with the capabilities of the frontier models that indeed look like they're perfect for some use case, and then to be hopeful that that happens all of the time. But in production, it is a folly. Gen AI models, you ask the same question twice or 5 times, you won't get the exact same answer 5 times. Sometimes it gives a completely wrong answer, and your software system needs to be resilient to handle the non-determinism, and also when there's a complete failure to deal with that gracefully.
And in this case, we started to treat all of our subcomponents and model dependencies that we took just as dependent microservices, which means all of the conventional software engineering practices like retries, schema validations, and fallback mechanisms, etc., were applicable here. Many of the models these days, be it reasoning models or such, actually do produce structured JSON. So that does help us do a great deal of, great deal towards helping treat them as dependent services.
So these were some lessons. They are not all the lessons, obviously. And even if you apply all of these lessons flawlessly, it doesn't really mean you'll go from nothing to something in production in 4 weeks. That's not how it works. So in order to do this, you need a lot of other infrastructure on the hardware side, on the software side, and in different places you can do different ways. With Voltage Park, we call it our AI factory. What we mean is it is a place where the input is enterprise data, the output is actionable business intelligence. So in that example, the input was raw feeds from video cameras, the output was actionable, usable alerts. And to pull this off, all you need is models, the right models. You need software that consumes the models. You need infrastructure, hardware and software, GPUs included. Now, everybody has a factory. How's our factory different? These are a few fundamental ways where I think we are thinking about this in a different way. The first way is it is very use case driven. It's not about let's stand up capabilities that can solve anything. Let's start with one use case that you're trying to solve. Let's talk about what is the minimal footprint needed to get something working in production. So our factory is minimal. It is very modular. You add more use cases, you can add the other incremental things needed, both in the hardware and the software, to take that use case to production. One of the places where we are different is because we run GPUs at scale. We've become fairly good at it. So then by adding world-class software engineering capability, we end up with a stack that's very tightly coupled. And the simple reason why this matters is to drive down cost. If you don't do it, it is impossible to take the dollar per token down to its asymptotic approaching zero. So that's how our factory is different. From a customer's perspective, many customers don't have the time, patience, or expertise to mess around with all of this themselves. To them, it's very simple. It's one phone number that they call. They don't care how it's working. It just works. There's one phone number they call. And this thing scales. It scales from a few GPUs to any number of GPUs. The architecture is the same. So in this example, you could start with feeds from 50 cameras, scale that to 500,000 cameras. The architecture is exactly the same. Thank you all. We'll be at the coffee station if you want to hang out.